Okay, I'm gonna hope this is recording already. So, good afternoon. Hopefully, you're watching this on Thursday and not using your weekend to catch up on stuff. So today we're going to start talking about lesson 2.2. This is one of the types of reasoning that we're going to talk about in this chapter, and this one's called inductive reasoning. We'll talk a little bit more about this as we go, but inductive reasoning is pretty much the type of reasoning that you use in science classes, or in science in general. I guess you're doing it in science class too, for sure, but scientists are really using inductive reasoning a lot. So we're going to talk about what inductive reasoning is, and then mostly what we'll be doing with a couple of these examples is following patterns. So again, this isn't really anything that's super tricky. The new thing here is recognizing that what you've been doing probably since grade school is inductive reasoning. And then we'll talk about the other type of reasoning later on, which is deductive reasoning. And the big goal will be what's the difference and why do we use one or the other in geometry. So we've got two vocabulary words here, inductive reasoning and conjecture. Those are going to be really important. Conjecture is a word we only use in math, but we'll talk about what that might look like in science too. So I don't often put these in here. You've seen a couple of them, but this is straight from your book. I think it's an excellent description of what inductive reasoning is, and so I just put it right in there. I couldn't do much better myself. So it says, as a child, you learned by experimenting with the natural world around you. You learned how to walk, talk, and ride your first bicycle, all by trial and error. From experience, you learned to turn a water faucet on with a counterclockwise motion and to turn it off with a clockwise motion. You probably didn't even notice you were doing that, but you figured it out in your head without really thinking about it. You achieved most of your learning through a process called inductive reasoning. And that is the process of observing data, recognizing patterns, and making generalizations about those patterns. So essentially, this is the type of reasoning that you have been using your entire life. You do this completely naturally, and there is no real thought on your end that has to go into this most of the time. It's just how pretty much any living thing figures things out. Anything that can think anyway figures things out. Because it's just a matter of noticing a pattern and kind of what works and continuing on with doing what works. So they give the example of riding a bike, and no one is able to completely explain to you the physics behind riding a bike that you would understand that when you first learned. But you notice the patterns of when you do this, it works, or when you do this, it definitely doesn't work, and you figured it out through basically trial and error, and that's what inductive reasoning is. So let's just quickly take a look at a couple of examples here, and then we'll talk about kind of where this gets used outside of just learning about your world and things like that. So here we've got an example here, a little more specific, concrete example that has like an answer and everything. So a scientist dipped a platinum wire into a solution containing salt. In this case, it's sodium chloride. Passes the wire over a flame and observes that it produces an orange-yellow flame. She does this with many other solutions that contain salt. Lots of different kinds of salts in the world. And she finds that they all produce an orange-yellow flame. And so we're supposed to make a conjecture based on these findings. Now, a conjecture is just something that we think is true. It's based on patterns. It's based on what we've seen in the world, data we've collected, whether it's formally like writing it down data or just informally by observation of what happens and what seems to be working. So if we dip a whole bunch of these wires in salt solutions and we burn them and they always make this orange-yellow flame, I think the logical conclusion there would be that salt solutions seem to create an orange-yellow flame when they burn. That's inductive reasoning. It's not something that is super complicated most of the time. It's just looking for a pattern, and when you see that pattern, inductive reasoning would say, I bet that pattern keeps going. I bet it continues on. Now, important things to note. Now I'll move my face over here. Does the scientist's observation prove that all solutions containing salt burn with an orange-yellow flame? And of course, it doesn't. Like, we've tried a lot of them, however many we've tried, 20, 30, whatever. But there's nothing absolutely proving that the 31st one isn't going to be blue. And so that's one of the limitations of inductive reasoning. It never proves something beyond every doubt. It can provide a lot of evidence for it. It can provide a lot of support, but it never actually proves anything. And so the question we always ask is, what would it take to disprove the conjecture, to prove that not all salts burn with an orange-yellow flame? It would just take one. one salt that doesn't burn orange yellow. We stick something in there and it turns blue. Hey, our conjecture was wrong, but that's how we learn. And this is exactly how science works, right? In science, we've never claimed to prove anything. Science is a matter of noticing patterns and collecting support for those patterns. Nobody is ever going to claim that they've 100% guaranteed have the right thing, but they've gathered evidence. By the time we're talking about something like evolution, right, we've got a ton of evidence. It's not changing anytime soon. We're really, really sure it's right, but we can't 100% prove it in that sense. But more and more evidence, we've certainly supported our hypothesis, our theory, our conjecture, those kind of words you kind of use interchangeably sometimes. But that's how science works, right? We have a hypothesis, we provide evidence, we support it, and eventually it comes to be accepted because it's overwhelming evidence that it is true. Now, in math, we're going to use inductive reasoning a lot. It's great for noticing patterns. I think at the beginning of class, beginning of the year, we talked about how math really is noticing patterns, looking for those patterns, describing those patterns. The one thing that we do differently in math is we actually do try to get to that prove word. It's not enough to just support with evidence and support with evidence and support with evidence until we're really, really confident that it's true. In math, we actually might start with inductive reasoning, but eventually we get to what we call deductive reasoning, and where we actually try to prove that something is true indeed. So in this class, what this is going to look like a lot is we're going to use inductive reasoning a lot. We're going to do some activities. We're going to look for patterns. I'm going to have you write those patterns down as what we call a conjecture, which is something that we think is true based on inductive reasoning. But eventually we're going to move on to what we call deductive reasoning, which we'll talk about in a little bit here, to prove a theorem. And that is something that we don't do in science because it's just not possible to do in science. Math in this case is a little bit more abstract, and we've started off with some things that we're claiming are true, and from there we prove the rest of them. So it's a little bit different way of thinking about it, but both are very, very useful. So let's go back and think about something that you've probably been doing for a very long time here, is just looking at patterns and seeing what comes next. So here we've got a pattern like 2, 4, 7, 11. And so we want to make a conjecture about what the rule is, what the pattern is, and eventually find the next few terms in this pattern. So a few things you're going to want to look at. If we're dealing with numbers, dealing with math, we're probably looking at something like using addition or multiplication or subtraction or something like that. And so we want to look for those kind of patterns. So take a look at like your first two numbers. To get from 2 to 4, it could be something like multiplying by 2, adding 2. We don't really know. But maybe we think about this as adding first. We're adding 2. Now to go from 4 to 7, we're not adding 2 anymore, but we're adding 3. To go from 7 to 11, now we've added 4. At this point, I think you're probably getting the pattern here. The next term is going to be found by adding 5. So it'd be 16. And then we might want to add 6. So that would be 22. If we add next one, we're going to add 7. So that would be 29. And we can just keep going. Most of these patterns are going to be pretty simple. They're going to be adding something. They're going to be subtracting something. They're going to be multiplying by something. But take some time and kind of play around with it. See what works. If the first pattern you try works for the first 3 numbers and not the fourth, well, that wasn't the pattern. Look for a different one. You find a pattern that works for the first 4 numbers, well, then you get to keep going. Now we could also look at this in terms of some shapes. So this one's a little bit more interesting here. We've got these seemingly very, very different shapes here. But there's some questions I want you to look at here to maybe help you out. So the first question is, what do you notice about the first, third, and the fifth shapes? And hopefully you've noticed already that those shapes are all circles. And what they appear to be doing, they look like they're turning. Each time they're turning, it looks like a quarter of a turn, 90 degrees. counterclockwise. You see that? Counterclockwise that way. I was probably backwards on your screen. Sorry about that. I turned it counterclockwise, I promise. It's just the camera flipping it around. And then you also might want to look at the second, the fourth, and the sixth term, and you're going to notice that those are all polygons. They've got these same exact 3 dots in them, and they're changing their number of sides. This one's a triangle, this one's a pentagon, this one's a heptagon, 7 sides. And yeah, they're all adding up sides each time here. Now, one thing it's really helpful to do on something like this is maybe look at the term numbers. So this would be the first term, second term, third term, fourth term, fifth term, sixth term, and see if that can help you relate to anything. So here, the second term is a triangle. The fourth term is a pentagon. The sixth term is a heptagon, 7 sides. I think for you, most of you hopefully can see that there's a connection there. There's a pattern in those numbers. For every even number term, the polygon has one more side than that number. And so that's going to help us out. So when we get to questions like, what do the next 2 shapes look like? Well, we can take this 5th shape and we can know that the 7th shape is going to look like that. And we just have to turn it again. So it's going to go that way with the shading on this side. If we go 3, 5, 7, well, I bet the next side has 9 sides. And I'm not drawing a 9-sided shape because, that's hard to do. I could probably figure it out. 1, 2, 3, 4, 5, 6, 7, 8. And I can't do it. Pretend that has 9 sides. And we'd have a dot up there and our circles down there. We're going to pretend, like I said, pretend it has 9 sides because, drawing polygon like that is hard to do. There we go. Now, when we want to answer questions a little bit further down, something like what's the 25th shape look like, or what does the 30th shape look like, then it's a little bit harder. We have to actually think about this pattern a little bit more abstractly, I guess. So if you want to start with question 5, I think that's the easiest one. So number 5, the 30th shape, since it's an even number, is going to follow this pattern. And we notice that every single time, the number of sides of that polygon are 1 bigger than our number. And so our 30th shape is going to have 31 sides. Definitely don't draw that. That would be miserable. Now, something like the 4th step, the 25th shape, that's not an even number. That is an odd number, which means we know it's got to be one of these circle things. It's going to be 1/2 shaded. And usually people try a couple of different strategies to figure this one out. One is you could just kind of turn it in your head over and over and over again, and eventually you'd get to 25. So 1 looks like this, 3 looks like that, 5 looks like that, 7 looks like that. But hopefully what you notice is what would happen once I get to the 9th term. And if we're taking this shape and we're rotating it counterclockwise again, the 9th shape actually looks exactly the same as the first shape. So 9 looks the same as 1. My battery in my pen is dying, sorry. So 9 looks like that. Then we've got our 11th shape that looks like that. Our 13th shape looks just like that. Our 14th shape looks exactly the same as the 7th. Not 14th, 15th. Only odd numbers. Then we go back 17, 19, 21, 23, and right back to where we started, 25. So the 25th shape looks exactly like the first one. And there's some extra math hiding in there if you really wanted to dig into it. But noticing that pattern again, that this thing just repeats over and over again, because every 4 times you turn it, you end up right exactly back where you started. So just got one conclusion question here. Are all conjectures that arise from inductive reasoning true? So you've noticed a pattern. You were correct. The pattern, I correctly identified the pattern. Is that guaranteed that pattern continues? Think about that for a second. You've noticed this pattern. You've noticed it over 100 times. It's held up. Does that guarantee that it works on the 101st time? Nope. So that is one of our downfalls of inductive reasoning. It only takes one new piece of evidence to show us that our conjecture wasn't quite right, and we might have to revise it. It probably means that we're close and we just have a little bit of revision to do. But that's usually where we're starting, is looking for those patterns and using inductive reasoning on those. Okay, so down below you, I think there's a few questions to answer as a quiz rather than doing it on paper as a homework assignment. So go ahead and do those. It shouldn't take you too long. I'm not going to put a bunch of questions. I just want to see if you know what inductive reasoning is. And I will see you all next week.